Hello everyone. In this lecture we will be talking about the convergence rates and global convergence properties of optimization algorithms, and also later on we'll discuss golden section. So let's talk about this definition of global convergence. The idea is very simple. It says that an algorithm is globally convergent if it converges to a locally optimal point starting from any point. Okay, so let's look at an example. So what this definition says is that no matter where you start from, no matter where you pick your initial point to be, x1, if your algorithm is globally converging, then independent of whether you start here or whether you start here, you would always converge to a locally optimal point. So different points, if you choose a different starting point, your algorithm may converge to a different point depending on the trajectory of the path, which is determined by the direction that you choose and also the step length that you choose. But an algorithm is said to be globally convergent if no matter where you start from, you always converge to some place. Okay. Now some algorithms may not be globally convergent. We will see in the next chapter that Newton's method is not globally convergent, and for such methods to work, you really have to pick your starting point to be close to the local minimum. So if I have a one-dimensional function and if I have a method which converges to the locally optimal point, provided that I start within some neighborhood of x star, then it is not globally converging. So in this picture, suppose I start here, and if I fail to converge to x star, but whenever I start within a certain interval, say this interval, I'm able to converge to x star. That means I can locally converge provided I am within a certain neighborhood of x star. Then that is locally converging and not really globally converging. So global convergence is different from global optimality. A global optimal solution is the one which is the best amongst all, which is the optimal solution over the whole real space, and not just locally optimal point. But when we talk about global convergence, we are still talking about locally optimal points, but this global is associated with the starting point and whether we are able to converge to a critical point no matter where we start from. Okay, so if an algorithm is globally convergent, then you can start from any point and you should be able to reach a locally optimal solution. Of course, if you start from a different point, you might end up reaching a different solution, but that's okay. That still means that you are globally convergent. So this is a very desirable property to have. That means the modeling person doesn't have to worry too much about suggesting an initial point to start searching, because you have some confidence in the algorithm that it will converge no matter where you start from. Okay, but the quality of the final solution will still depend on whether you started somewhere close to a good solution or you started close to a somewhat of a poor solution which is locally optimal. Okay, so we will go to the next idea, which is the idea of convergence rates. Of algorithms. So a convergence rate tells us how fast an algorithm will converge to the desired point. This is also an important useful property to have. So when you are designing algorithms, one is you would like to make sure that the algorithm is correct and that it converges no matter where you start from. So you would like your algorithm to be globally convergent, but also you would like to count the number of iterations your algorithm takes. Now, convergence rates do not count the number of iterations. Rather, they give an abstract idea of how fast the algorithm is converging, independent of the problem size. So here we don't really worry about whether there are 20 variables or 100 variables or 1000 variables. Of course, as the number of variables and the complexity of the nonlinear function increases, your algorithm will take more and more time. But time is not something we are worried about, at least technically speaking. We are more worried about the relative speed at which the iterates converge to x star. So let's start defining this. Let x star be a desired point, or be the limit point of a sequence x1, x2, so on and so forth. So now we are interested in finding how fast is this sequence going to go close to x star. So one way of understanding how close we are to x star is to just look at the distance of individual points of the sequence to x star. So we say an algorithm is linear if the distance change in the distance in the new iteration as compared to the distance covered in the previous iteration is less than or equal to a. Okay, where a greater than 0 is a constant. Okay, so so here I'm comparing actually I'm sorry, let's go back. So I'm not talking about the distance traveled in every iteration, I'm talking about the distance from the optimal. So this part is important and easy to get it wrong. I'm sorry about the earlier mistake. So we say a function is linear if the distance from the limit point, and if I take the ratio of distances to the limit point between two consecutive iterations, that is less than or equal to some constant a which is positive and constant doesn't depend on k. Okay, and this must hold for every k. Okay, big enough. So for all k, let's say greater than or equal to some capital K. So after several iterations have passed, then eventually your algorithm should settle down to this this sort of improvement. So usually a is less than 1 here, because if a is more than 1, then you might actually be diverging. So usually a is less than 1, and lower the better. So let's look at an example of linear convergence. Let's say we have iteration number, and so this is k, and xk minus x star So let's say in iteration 1 I'm at a distance 1 from the limit point of my sequence, and a is, let's say, half. So in the second iteration the distance should become less than half of what it was earlier. So let's say it becomes half, and then the distance should become less than half of what it was earlier, so on and so forth. as you can see that with every iteration my distance is becoming half. So this is a good rate of convergence. It is sort of decaying, your error term is decaying exponentially with iterations, which is nice. However, if a is close to 1, then this decrease is fairly slow. There are other notions of convergence as well. So let's look at another important class of convergence rate, which is superlinear convergence. Again, like linear convergence, this is a definition applicable to a sequence of points which converges to a certain point, say x star. So suppose the sequence x1, x2, xk, so on and so forth, converges to x star. We say it converges superlinearly if this distance ratios, so again xk plus 1 minus x star, the distance upon the distance of the previous iterate, this decreases with every iteration. So remember that in a linear convergence, this ratio has to be less than or equal to a certain fixed constant. But in superlinear convergence, we are trying to even reduce that fixed constant in every iteration. So this is heading to 0, limit k going to high. So what this is saying is that eventually your distance to the limit point has to be significantly much less than the distance earlier. So it's easy to show that superlinear convergence implies linear convergence. So everything that is superlinearly converging is also linearly converging, but the converse is not true. Okay. We also have the notion of quadratic convergence. Which says that the distance of the new iterate, just like linear, as compared, should be less than or equal to a, but we also have a square term in the denominator. Okay, so if this holds where a is greater than 0, and here a need not be less than 1, it can be more as well, but what we want is the ratio of the current distance to the square of the distance of the previous iteration should be bounded by a positive number. So let's go back to our example and try to see how does quadratic convergence fare as compared to linear convergence. So this is, let's say, linear. Let's try to understand these values for quadratic convergence. So again, let's see if we can find what this means. Is in the first iteration, let's say I start with this, again it's assumed. So in the next iteration, if my sequence is converging quadratically, then in the next iteration this distance better be half, okay, because then then I satisfy the definition of quadratic convergence. So so this is quadratic and this is my linear. What would happen, what should happen in the third iteration is that this number should go down to 1/8. Because when I divide 1/8 by the square of this term, I will get half. Okay, so already in the third iteration we are going a bit faster than the linear case. In the next iteration 4, this number should go down to 1/128. Okay, because again, if I divide this number by the square of this number, I'll get half. Okay, so as you can see that this quadratically converging sequence is falling fairly drastically as compared to the case where we don't do it. So so quadratic, so what would be the next next term here would be so I want 1 by something, so that when I divide by the square of this term, I should get half. Okay, so so it will be a fairly big number here. So you can try to fill this up. Just apply the definition and get it. Okay. So the only worthwhile thing to remember is that here A is half. Okay. So quadratic convergence is blazing fast as compared to linear convergence. Quadratic convergence is also faster than superlinear convergence. So this is really the fastest type of algorithms that we will see. Where does line search lie? So let's talk about our method that we studied in the previous lecture. Line search, both exact and inexact. First is it converges globally. That means you can start from any point and your steepest descent and line search would take you to the minimum eventually. Okay, And the second important result about line search, the steepest descent, is that it converges linearly. Okay, or at least, or at most, linearly, in the sense that the book has an example where it doesn't converge superlinearly or quadratically, but it does converge linearly. So we can say that line search is either linear or slower than linear convergence. Okay, because the book has an example, exercise to show that line search is linear in certain cases. So line search is a nice method because it converges globally. It is also nice because I only want gradients. I don't need Hessians, which are a bit more tedious to compute. And the second property we have is that line search along steepest descent with exact or inexact step length search converges linearly, which is not that great. We will get faster algorithms later in the course. So with this, I would like to stop, and in the next part we will continue with some bucketing and sectioning for finding the right step length.